Hello, welcome back. So in this part, we will discuss what is the kind of nature of force which is being acting on the steel beam. Well, generally we assume that the beam is subjected to transverse loading only. As I said, that beam may have inclined load also, but in our case, what we will do is we will assume that it is carrying this vertical load only, which is completely transverse. Because in case of inclined load, some part of, uh, some component of the load will be vertical and some component of this load will be horizontal. So in that case, if a beam is subjected to the transverse loading as well as along the longitudinal section, in that case, the beam will be termed as beam column, which means the magnitude of the transverse and axial load will be significant. So basically what we do is we will assume that our beam will subject to this transverse load only. So that is the one thing. Now the second point which is there is all the loads and sections lies in the plane of symmetry. For example, this is the I section and this is the Z axis and this is the I, Y axis. So you can see this I section is symmetric about the Z axis or about the Y axis. So basically on this I section, load will be like this one. So this I section symmetry and the load direction both are in the same plane. So that is why we are saying that we assume that all the loads and the sections lies in the plane of symmetry. So that is again our assumption. Now next, also it follows that the beam will be primarily subjected to bending and shear. So the primary effect or the main effect of the load will be in terms of bending and in terms of shear in the loading plane with no external torsion and the axial force. As I said that we won't consider the vertical load. We will consider only the vertical load. We will not consider the inclined load acting on the beam because inclined load will induce axial force also. So basically our assumption is that there is no external torsion and there is no axial force. The effect of load will be primarily based on the bending and in the shear. But here is to be mentioned that the problem of torsion cannot be avoided completely, even the section shape is symmetrical. Basically, as I discussed earlier also, uh, there is a term which is called shear center. So in case of doubly symmetric section, like the I section is symmetric about the Z axis and along the Y axis. So this I section will be called as a doubly symmetric section. So in case of doubly symmetric section, the shear center and the CG of the section will be at the same point. So if we allow or if we apply the load along this shear center, then we will assume that there will be no torsion. Similarly, if there is a singly symmetric, for example, the channel section. So channel section is symmetric about the Z axis, but it is not symmetric about the Y axis. So in that case, in that case, the shear center and the CG, like CG of this channel section will be here, but the shear center of this channel section will be somewhere here. So which is not on the same point. So in that case, if we apply load along the shear center, then we can assume that this channel section will not be subjected to the torsion. Well, that is our basic assumption. Even but even if we use doubly symmetric section and if we apply the load along the shear center, even then also we cannot avoid the problem of torsion completely because of the other parameter. Now, what is that other parameter? That other parameter is the instability. Because in case of I section or doubly symmetric section, there may be a term which may occur which is the instability. And this instability is caused by the compressive stress. As I said, beam will be subjected to the compression and tension as well. Like this is the I section and this is the neutral axis. So below the neutral axis, the beam will be in tension, and above neutral axis, the beam will be in the compression. Now, the above part, the upper part of the beam will be subjected to compression, and this compression force will cause the instability, and this instability will cause this beam to rotate about the longitudinal axis, which is actually the torsion. Now we will see this instability in more detail using the diagram in the next slide. But that is the main criteria which generally is being considered while designing the beam. Now, such instability, as I said, that this instability is caused by the compression force, because of this load, this part will be in very high compression, and because of this compression, this beam will try to buckle like this. This web will try to buckle like this, while the lower part of the beam will be in the tension, and this tension force will try to place. I mean, will try to fix at its own position, and in that scenario, as because the compressive force has the tendency to the buckle to buckle the section, so in that case the beam may buckle from like this. It may rotate from the upper part like this. I will be showing you that using the diagram how it will be buckling, and this kind of buckling is called the lateral buckling. Now lateral buckling can I mean, when the buckling is involving only the local component of the beam. I mean, if the beam is buckling, if the beam is buckling along the only along the a small part, then in that case we call it local buckling. And if the whole beam is bending or buckling, in that case we call it the uh, the lateral buckling. Basically, if this is the beam, if this is the beam, something like this, and because of this load, if it is bending, if it is deflecting like this, then we call it bending. This deflection is because of the bending. But when this beam is rotating like this, because of the lateral effect, in that case this is called the lateral buckling. So generally, ideally, we want the effect of force in terms of this bending only, because that is the part that we will consider in our design. But considering the effect of lateral buckling, it will be very complex and very difficult to calculate the actual strength of the beam considering the lateral buckling. So I will discuss more about it in the next slide. Basically, this buckling, this local buckling is the function of the width to thickness ratio. Well, width here is referred to as the width of flange to the thickness of web. So basically, if the ratio of width of flange to the thickness of web is very high, in that case, the chances of local buckling will be very high. If this ratio is low, then the chances of lateral buckling will be very low. Now see in this diagram, consider that this is a simply supported beam and it is subjected to this point load, and because of this point load the beam will deflect like this. Okay, now if we cut the section, then this at this section you can see this is the original position, and because of the bending the beam will bend, deflect downward, and the position now is here. Now after this the beam may be subjected to the lateral buckling, and because of that you can see the beam is twisting. And the same phenomena you can see here also. So you can see this is the vertical bending, vertical deflection, and this is the horizontal deflection. I mean, this is the original position and this is the final position. So you can see here the beam is deflecting vertically as well as horizontally. So this horizontal displacement or horizontal movement of the beam is very harmful. I mean, if we consider the effect of this horizontal deflection, then calculation of the beam strength is very complex. And based on this, we have divided our beam in two categories. Now, if we fix the upper flange, if we fix the upper flange of the beam, in that case, this horizontal deflection can be prevented, because this beam will always try to rotate from the upper position, because on the upper end the beam is in compression and on the lower side beam is in the tension. Well, tension is not as such causing this rotation. This rotation is actually caused because of the compression in the upper part of the neutral axis. So based on this, we can have two types of beam. One is called laterally supported beam, which means if we fix this upper flange of the beam, in that case, beam will not twist, it will not have torsional effect, and the beam can be designed simply, optimally, and the strength of beam will be high if we support it laterally. And if the beam is not supported laterally, like this is the case, in that case we will call it laterally unsupported beam. So in our scope we are restricted ourselves to the first case, so we will design our beam only as a laterally supported beam. We will not consider the phenomena of laterally unsupported beam, that is not in our scope. So we will design only the laterally supported beam. Now, how do we laterally support the beams, that we will see. Well, if we are using beam as a I section, so if we fix this upper flange in the floor, now floor may be of concrete, so if we fix this flange in the concrete, in that case this flange will not try to rotate like this. So what we have done is we have fixed it laterally. Similarly, other method can be if we use the connectors, like these are the shear connectors, and these shear connectors are being embedded into the concrete floor. So this is basically the concrete floor, and flange along with the shear connectors is being embedded in that. In that case, the resistive power, the resistance of this upper flange will be very high, and it will not be able to twist like this one. Similarly, there may be other method also, like if there are two I sections, in that case in between them we can use as a diaphragm wall. So this diaphragm steel plate can be used in between them to prevent the twisting, or sometimes we can use cross bracing. So there may be several methods, there may be so many methods which can be used uh, to prevent this, to fix the upper part of the beam, because buckling will occur, the lateral buckling will occur from the upper part, because upper part is subjected to the compression. So the part which is subjected to compression, if we fix that laterally, then there will be no twisting. So that is the main phenomena. So we will discuss our lecture in the next part. Thank you.